Umami, a savory taste, is one of the 5 basic tastes. A loan word from the Japanese, umami can be translated as pleasant savory taste. This particular writing was chosen by Professor Kikunae Ikeda from umai delicious, and mi taste. The kanji, y cubed are used for a more general sense of a food as delicious. People taste umami through receptors for glutamate, commonly found in its salt form as the food additive monosodium glutamate. For that reason, scientists consider umami to be distinct from saltiness. Background: scientists have debated whether umami was a basic taste since Kikunae Ikeda first proposed its existence in 1908. In 1985, the term umami was recognized as the scientific term to describe the taste of glutamates and nucleotides at the first Umami International Symposium in Hawaii. Umami represents the taste of the amino acid L-glutamate and 5 unregistered trademark ribonucleotides such as guanosine monophosphate and inosine monophosphate. It can be described as a pleasant brothy, or meaty taste with a long-lasting, mouth-watering and coating sensation over the tongue. The sensation of umami is due to the detection of the carboxylate anion of glutamate in specialized receptor cells present on the human and other animal tongues. Its effect is to balance taste and round out the overall flavor of a dish. Umami enhances the palatability of a wide variety of foods. Glutamate in acid form imparts little umami taste, whereas the salts of glutamic acid, known as glutamates, can easily ionize and give the characteristic umami taste. GMP and IMP amplify the taste intensity of glutamate. Discovery of umami taste. Glutamate has a long history in cooking. Fermented fish sauces, which are rich in glutamate, were used in ancient Rome. In the late 1800s, chef Auguste Escoffier, who opened restaurants in Paris and London, created meals that combined umami with salty, sour, sweet and bitter tastes. He did not know the chemical source of this unique quality, however. Umami was first scientifically identified in 1908 by Kikunae Ikeda, a professor of the Tokyo Imperial University. He found that glutamate was responsible for the palatability of the broth from kombu seaweed. He noticed that the taste of kombu dashi was distinct from sweet, sour, bitter and salty and named it umami. Professor Shintaro Kodama, a disciple of Ikeda, discovered in 1913 that dried bonito flakes contained another umami substance. This was the ribonucleotide IMP. In 1957, Akira Kuninaka realized that the ribonucleotide GMP present in shiitake mushrooms also conferred the umami taste. One of Kuninaka's most important discoveries was the synergistic effect between ribonucleotides and glutamate. When foods rich in glutamate are combined with ingredients that have ribonucleotides, the resulting taste intensity is higher than the sum of both ingredients. This synergy of umami explains various classical food pairings, starting with why Japanese make dashi with kombu seaweed and dried bonito flakes, and continuing with various other dishes. The Chinese add Chinese leek and Chinese cabbage to chicken soup, as in the similar Scottish dish of cock-a-leekie soup, and the Italians combine Parmesan cheese on tomato sauce with mushrooms. Properties of umami taste. Umami has a mild but lasting aftertaste that is difficult to describe. It induces salivation and a sensation of furriness on the tongue, stimulating the throat, the roof and the back of the mouth. By itself, umami is not palatable, but it makes a great variety of foods pleasant, especially in the presence of a matching aroma. But like other basic tastes, with the exception of sucrose, umami is pleasant only within a relatively narrow concentration range. The optimum umami taste depends also on the amount of salt, and at the same time, low-salt foods can maintain a satisfactory taste with the appropriate amount of umami. In fact, Roynan et al. Showed that ratings on pleasantness, taste intensity and ideal saltiness of low-salt soups were greater when the soup contained umami, whereas low-salt soups without umami were less pleasant. Some population groups, such as the elderly, may benefit from umami taste because their taste and smell sensitivity is impaired by age and medicine. The loss of taste and smell can contribute to poor nutrition, increasing their risk of disease. Foods rich in umami. Many foods that may be consumed daily are rich in umami. Naturally occurring glutamate can be found in meats and vegetables, whereas inosinate comes primarily from meats and guanylate from vegetables. Thus, umami taste is common to foods that contain high levels of L-glutamate, IMP and GMP, most notably in fish, shellfish, cured meats, mushrooms, vegetables or green tea, and fermented and aged products. Many humans' first encounter with umami is breast milk. It contains roughly the same amount of umami as broths. There are some distinctions among stocks from different countries. In dashi, L-glutamate comes from sea kombu and inosinate from dried bonito flakes or small dried sardines. Taste receptors. Most taste buds on the tongue and other regions of the mouth can detect umami taste, irrespective of their location. The tongue map in which different tastes are distributed in different regions of the tongue is a common misconception. Biochemical studies have identified the taste receptors responsible for the sense of umami as modified forms of mGluR4, mGluR1 and taste receptor type 1, all of which have been found in all regions of the tongue bearing taste buds. The New York Academy of Sciences corroborated the acceptance of these receptors, stating, "Recent molecular biological studies have now identified strong candidates for umami receptors, including the heterodimer T1R1 Patum 103, and truncated type 1 and 4 metabotropic glutamate receptors missing most of the N-terminal extracellular domain and brain mGluR4. Receptors mGluR1 and mGluR4 are specific to glutamate whereas T1R1 plus T1R3 are responsible for the synergism already described by Akira Kuninaka in 1957. However, the specific role of each type of receptor in taste bud cells remains unclear. They are G-protein-coupled receptors with similar signaling molecules that include G-proteins beta-gamma, PLCB2 and PI3-mediated release of calcium from intracellular stores. Ca2+ activates the selective cation channel transient receptor potential melastatin 5 that leads to membrane depolarization and the consequent release of ATP and secretion of neurotransmitters including serotonin. Cells responding to umami taste stimuli do not possess typical synapses, but ATP conveys taste signals to gustatory nerves and in turn to the brain that interprets and identifies the taste quality. In popular culture, umami has become popular with food manufacturers such as Nestlé Copyright, the Campbell Soup Company and Frito-Lay. Farmers promote their produce as a way to boost umami taste, and chefs create umami bombs, which are dishes made of several umami ingredients. Malcolm Gladwell discussed umami as a key factor accounting for the sustained formulation and popularity of ketchup. References, notes. Citations. External links, Umami Information Center, International Glutamate Information Service, Italian Umami Research, Discovery of Umami Receptors, Society for Research on Umami Taste, Who's Umami? Human taste now comes in 5 flavors, CBC News, June 1, 2007, sweet, sour, salty, bitter and umami. NPR, November 1, 2007, A New Taste Sensation, by Katie McLaughlin, Wall Street Journal, 1207. Mouthfuls, Whitlock is Another Basebill, 2408. The Science of Taste at Kitchen Giekery. An informative article about the science behind taste, including umami. Written from a culinary science perspective.